Hello everyone, this is for section 9.3 for pre-calc. It's on geometric sequences. Again, a sequence is a list of numbers. This is what makes a geometric sequence a geometric sequence is that the terms have a common ratio. And the formal definition looks like this. And what you need to notice from it is that you're taking a particular term and dividing it by the one that came before it. A particular term and dividing by the one that came right before it. That gives you the common ratio. And I'll talk more about that here, and I'll give you an example. How about 2, 4, 8, 16, and so on. I pick a term and divide it by the one that came before it. Pick a term and divide it by the one that came before it. So its common ratio is 2. The common ratios can be negative. If I pick a term and divide it by the one that came before it, pick a term, divide it by the one that came before it, they also can be fractional. So let's say you had 2, and then how about 1, and then a half, and then a quarter, and so on. Pick a term and divide it by the one that came before it. Pick a term and divide it by the one that came before it. Okay? And that could also be negative. All right? So they have a common ratio. The explicit formula for a geometric sequence is going to be given by this, where it's your first term times your common ratio raised to the n minus 1 power. To get a partial sum, say I want you to add up the first 20 terms in, say, this sequence. This would be the formula. This is supposed to be 20. Your first term times 1 minus the common ratio raised to n over 1 minus the common ratio. When you guys use it, what you guys will need to do is you'll need to input a second set of parentheses around this when you go to type this in your calculator. Same deal down here. You're going to have to insert another set of parentheses. Okay? One thing that you guys haven't done before is an infinite sequence of numbers. So say, for example, this sequence goes on forever. This one goes on forever. What's the sum? Well, it turns out for those two, there wouldn't be a finite number that it goes to, whereas this one it would, and we'll talk more about that here. That's what this reference is here, that your common ratio in absolute value has to be less than or equal to 1 in order to get an answer from a geometric sequence that's infinite. And we'll talk more about that as we get towards the later slides in this section. Okay, I think that's all there is there, yep. Okay. I'm asking, are these a geometric sequence? Well, you pick a number and divide it by the one that came before it. So that'd be 15/9, so divide by 3, so 5/3. Pick another set of numbers. I'll go with this one, that'll be easier. 18/6. Well, you just get 3. These aren't the same number. This isn't geometric. Is this one? Okay, pick a number. Pick another number and divide by the one that came before it. You get the same number. So yes, that's a geometric sequence. Its common ratio would be -2. I think that's all of them on there. Yep. Okay. Given this information below, write the explicit formula and find the first 5 terms. Okay, so here's the pattern for a geometric sequence. A sub 1 is 1, so A sub n is equal to 1 times the common ratio is a half. Because it's a fraction, I need to put it in parentheses, raised to the n minus 1. Okay, do I really need the 1 sitting out front? Nope. So that would just be a half n minus 1. Okay, now it said find the first 5 terms. So a sub 1, you know, it's 1. They tell you it. A sub 2, take a 2 and fill it in. So a sub 2 is equal to a half to the 2 minus 1. So that's a half raised to the 1, so it's a half. A sub 3, so a sub 3 is equal to 1/2 to the 3 minus 1, which is 1/2 squared, which is a quarter. And so on. A sub 4, so a sub 4 is equal to 1/2. 4 minus 1 is 3. So that's an eighth. and a sub 5, same deal, fill it in. So that would be a quarter. Whoops, I got carried away. A half raised to the 4th power, which is 1/16. 1 over 16. Now you guys also could do this recursively. If you multiply each term by the common ratio, you get the next term. So the previous term I meant to say. Okay. So a sub 3 would be a half times a half is a quarter. So I'm doing this recursively. Take your previous answer and multiply it by the common ratio. This would be recursively. I'm taking the prior term and multiplying it by the common ratio. Okay? So in a situation like this, you could just continue to multiply the previous term by the common ratio. That's recursively. You had to know the previous term to get the next term, or you could do it explicitly using this formula. Like if I wanted the 15th term, I could just plug in 15 minus 1 would be 14. But if I want the 15th term doing this, I got to know the 14 terms that come before it before I get the 15th term. So that's what makes explicit nice, is that you can just jump in and find a term. But if you're actually generating, say, the first 5 terms, I think doing it recursively is easier. Okay, so food for thought, something to think about. Find the sum of the first 10 terms given the sequence. Okay, so the formula S sub n for a geometric sequence is a sub 1, 1 minus r to the n, over 1 minus r. So what I need to know is a sub 1. I need to know the first term. I need to know the common ratio. All right, so looking at this, the generic pattern for, or explicit pattern for a geometric sequence is this. So a sub 1 is the first term, or sorry, right there. Yeah, it is the first term, but it's right there. So r is equal to 3. I need a sub 1 and I need r in order to do this formula. So s sub 10 is going to be your first term, a sub 1, 1 minus 3 to the 10th over 1 minus 3. That I'm just filling in these numbers. Okay, a 3 would go there and there. I'm adding up the first 10 terms, so that's n. Whatever is here goes here. And then you would just type that in your calculator and get an answer. Remember, in order to get this to work in your calculator, you need to put a second set of parentheses here and here. Okay? As well as, I mean, keep the blue ones, but I'm saying these additional parens. All right? And that'll give you your answer. Okay, an infinite sum. That's what we want to work on here. Say you guys have a square that's 1 foot by 1 foot. You know the area of this whole thing, length times width, or sides squared, whichever way you want to do it, is going to be 1 square foot. All right. So let's say I take half of this and set it aside. I got a half a square foot. What remains is a half of a square foot. I'm going to take half of that, which is a quarter of a square foot. Because this was a half and I took half of it, so it's a quarter. I'm going to take this piece up here. If that was a quarter, and now I have an eighth, I set aside an eighth of it. And then I'm going to cut, so this would be an eighth. I'm going to take half of that and set it aside. So I added a 16th of a square foot. Take half of that, 16th. I added a 32nd, and so on. If I stop at any point, let's say I added up the first 20 terms in the sequence, I don't have everything, so I don't have 1 square foot. But let's say I could continue this pattern forever and continuing setting pieces aside, never stopping, never ending. What would that sum be? Well, by saying I'm going to do an infinite sum, it's assuming that I've been able to add up every last piece. There is no piece that I haven't added on yet. I know that sounds a bit ridiculous, but that's the idea of adding an infinite sum. You've added everything up. Physically, you're thinking, okay, I need to keep cutting little pieces and little pieces and little pieces. I understand that. But that's not jiving with, that's not the idea, that's not the heart and soul behind doing an infinite sum. An infinite sum assumes you've done everything. You've cut every piece off and added every piece on. If I've done that, doesn't it all the pieces have to add up to this whole thing? So the infinite sum has to be 1 square foot because I've added everything up. Okay? That sometimes this is a hard concept to get your head around, an infinite sum, because you've never done one before. I mean, if I just go 2 plus 3 plus 4 plus and so on, how could I continue to do this forever? How could I add an infinite string of numbers? If it's infinite, isn't there always one more to go? And if I add that one, then there's one more after it because it continues? Yeah, that is a weird idea, but we need to start grasping with it and getting your head around it, because adding an infinite sum is the foundation behind doing calculus. It is the precursor to everything that happens in calculus, is the idea of an infinite sum. Taking something and cutting it up into an infinite number of pieces and then adding those pieces up to see what the whole is. Okay, so here goes. Find an explicit equation for the sequence I just did on the previous page. Well, remember the formula for it, a sub n is equal to a sub 1 times r to the n minus 1. So I need to find the first term and then the common ratio. So a sub n is equal to the first term, well, we got it, it's written right there, a half times, now what's the common ratio? A fourth divided by half, 2 over 1, that reduces to a half. If I pick any other one, 1/32 divided by 1/16 times 16 over 1, that reduces and gives you a half. The common ratio is a half. Now, what you guys should recognize, this can be simplified. The base is the same, you're multiplying, so you add your exponents. This pattern is really, to simplify it, is a half to the n. Okay? Now, to find the sum of the first 20 terms, you use the pattern. So that was just, okay, so we've got the explicit equation. There it is, boom. All right. Now, you want to add up the sum of the first 20 terms. So that's going to be the formula, a sub 1, 1 minus r to the n over 1 minus r. So the first term, even if we didn't have this formula, is a half times 1 minus the common ratio, which is a half, and I'm going to raise that to the nth power. Well, I'm adding up the first 20 things, so I put a 20 there, and divide it by 1 minus a half. Close the paren, and I think I did this ahead of time. Let me make sure so I can actually write a number down for you guys, so in case you wanted to play along at home. Let's see, turn the time. Oops, it looks like I didn't type it in. So, yeah, I could type it in, but I think in the interest of time and not making this video as long as possible, I'll let you guys just type that in. Remember that you're going to need the second set of parentheses here to capture that, and a paren here to capture it, unless you type in a half on the bottom. You could also just type in 0.5 on the bottom. Okay? Now, that would give you the sum of the first 20 terms of the sequence. Oh, I remember it was like 0.99999 and then 024, something like that. Okay? But the point being is it didn't come out to 1. Now, assuming you can do an infinite sum here, you would use the formula for doing an infinite sum. So what we're doing is this. We're adding up every single piece in this puzzle. Or in that square, I shouldn't call it a puzzle. The formula for an infinite sum is actually really easy. A sub 1 over 1 minus r. Okay, a sub 1 is a half over 1 minus a half. So that's a half over a half, which is 1, which is what we said it should have been on the previous page. That if you could add everything up and that you've never stopped, you assumed you've done this forever, What should you get? Just intuitively, you've added up all the pieces of this thing. Well, here, using the formula, there it is. Okay. The one last idea is we're going to just lay the foundation with this, because what's going to come up later, and we'll talk more about it in class. It's going to come up with more what we're doing when we finish up with fourth quarter, start doing exponential calculus. Zeno was a guy that was an ancient Greek, and he liked to have arguments with people. And here's how it goes. You guys have heard of the tortoise and the hare before. The deal was the rabbit was really fast and the turtle is slow. And the turtle said, okay, I'm going to race you on this course, for however long the course is, but you need to give me a head start first. And the rabbit's like, not a problem. So let's say the turtle said, I want a 10-foot head start. The turtle's like, no problem, I'm still going to win. Okay, it's not really a contest. And the turtle says, no, wait a minute, think about this. In order for you to catch me, you're going to have first travel half this distance. In order to even come up, you're first going to have to go halfway. Okay, that sounds fine. But in that amount of time that it took you to go halfway, yeah, I'm slower than you. I will have moved forward a certain distance. So now the distance between us is this far. This is the distance that's now between us. Sure, it's closer, but there's still a distance that's between us. And in order for you to catch me, you're going to have first cover half the distance to me. And the turtles or the rabbit's like, yep, not a problem. But in that time, I will have moved forward. Sure, it's a smaller distance than I moved forward before, but this is now the new distance that's between us. It's smaller, but there's still a distance there. And in order for you to catch me, you're first going to have to travel half that distance. And in that amount of time, I will have moved forward again. And this would go on forever. That in order for you to catch me, you first have to cover half the distance to me. And in that amount of time, I will have moved forward a given amount. Sure, it's less each time that I will have moved forward, but nonetheless, I will have moved forward a certain amount. So, you'll never be able to catch me, because I will always have moved forward in the time it took you to cover half the distance to me. And so without ever the race starting, the rabbit gave up and said, you're right, there's no way I'm going to be able to win this race. Okay, so another way to describe this is, let's say this is a wall and you got a door that's in it, and you're standing over here. In order for you to walk out that door, you first have to cover half the distance to the door. Then, to walk out the door, you're still going to have to cover half the remaining distance, and half the remaining distance, and half the remaining distance. And so Zeno went on to argue, no movement is possible, because in order to achieve a distance that you want to walk, you first have to cover half the distance, and then half the remaining, and half the remaining. And there's always going to be a piece left. You're never going to be able to cover all the pieces, so you can't move. Everyone's fixed. Well, of course, you know that that's not possible. You've walked out of many doors in your life. But that's the idea that Zeno talked about, and that's one of the things that we're going to continue to talk about. So that ends this discussion on Zeno's paradox. There we go. Say.